Dear participants, welcome back to the second talk, okay, of in the third day of this STC. Okay, we have with us Professor Krishna Swami T. Selvan from SSN College of Engineering, Chennai. I have very brief bio about him because he's, if you want to know more about him, you can visit his website and then get the information. He completed his BE honors from Madurai Kamaraj University in 1987, and he did his MS from BITS Pilani. Okay, PhD from Jarawpur University, very famous university from Calcutta in 2002. He's got another postgraduate certificate in higher education from the University of Nottingham, UK. He worked with Samir Chennai, and also he worked with the University of Nottingham in its Malaysia campus. He was a research visiting scholar at the George Green Institute for Electromagnetic Research, and he joined in with the SSN in 2012. Dr. Selvan's teaching and research interests include electromagnetics, antenna theory, design, and measurements. It's a great pleasure for us to invite Professor Selvan to present his lecture on teaching electromagnetics in modern times. Professor Selvan, please.
Yeah. Thank you, Professor Subramanian, and thank you, Professor Krishnamurthy, for this invitation. It's always a pleasure to talk to and engage with faculty. I interact with faculty, so I look forward to our interaction today. So as the coordinators have said, please feel free to ask, interrupt during the course of the lecture itself. Don't have to wait until the end to share thoughts. Like I'm going to share some teaching methods, and some of you might be doing better. I mean, these are all some techniques which you can contemplate, and of course, some of you may already be doing also. Just based on my experience, just to share some thoughts. So the talk is titled Teaching and Learning Electromagnetics in Modern Times. The broad objectives for today's talk are, so the broad objectives are to discuss the challenges facing teaching in higher education in modern times, not necessarily electromagnetic specific, general challenges. And also, of course, to look at EM specific challenges. And then to discuss some possible approaches and to suggest some methods of nourishing and promoting EM education, which is what, electromagnetics is what has brought all of us together in this session, in many other programs. So how can we nourish and how can we promote? So sharing some ideas on these would be the objective for today's presentation. So what are the learning and teaching challenges in modern times? And this discussion, this slide is independent of whether it is electromagnetics or any other subject that we are teaching. One is, as all of us would be aware, the distractions, the kind of distractions students, modern students face, that is most unusual. Like, because some of us think that when I was a student, when I was a student, we were all very sincere and all, but we did not have, 30, 40 years, 20 years back, we didn't have the kind of distractions. And mobile represents the entire distraction. Mobile is a big advantage, and mobile is also a big distraction. Facebook, WhatsApp, Google, as we were talking some time back. So it is very difficult for students to pay attention for a long time, and we all admit that attention span are shrinking, and no surprise, no, it is not at all surprising. When distractions are too many, then obviously attention span reduces, is it not? And a consequence is impatience, looking for like fast food. Today's is fast food society we talk of, and whatever we see in as a social phenomenon, like filter coffee is in many places replaced by instant coffee, and then noodles kind of generation, and obviously this culture also gets into academia. So this is maybe it's a social challenge which is also manifesting in education. Therefore, though we all often talk of teaching challenges, but we should also realize that there are learning challenges as well. So students are, undergoing a lot of pressures, because once your distractions, all that social media and all puts on us, that is really a terrific experience to face. So now, obviously, the onus is on us, because we are elders as teachers. We are elders, therefore, we can't be complaining too much about students being distracted, because that's how the life is. Therefore, obviously, challenges follow. So how do we, it's a very complicated problem, but then as teachers, we do have much more responsibility than students themselves in trying to tackle this, and to see how best we can improve teaching learning process. I think this is something I want, especially my younger academic colleagues, to understand that students also have challenges in learning. So, in addition to this, these of course characterize entire gamut of especially science and engineering education, and there are also EM specific challenges. If you see in the last few years, especially, there has been a tendency to sort of shrink the curriculum, to reduce the credits. I think now it is some 150, 160 credits. But earlier, 5-year course, for some time, for several years, it was 5 years course and all, and annual pattern. Now there is a tendency to reduce the curricular content. And alongside, we also have several new technical advances presenting newer directions. Therefore, it has become necessary to accommodate those emerging areas also into curriculum. So on the one hand, curricular width is shrinking because of, again, a lot of reasons, including educational and social and cultural reasons, may not be cultural, social and educational reasons. Then these advances are also there. Therefore, there is highly competing demands. And in this, now when something new comes, we always look for something old to give space. And electromagnetics, not only, one of the reasons for people seeing electromagnetics as particularly old-fashioned is probably because of it's being considered as a difficult and abstract subject, maybe. So because student comments have begun to be taken very seriously, the West and also to some extent in India. So obviously there are pressures on academia to, to prune courses, to introduce, to bring in new. Therefore, electromagnetics being already perceived as a very abstract and complex subject, and then a new thing is also coming. Therefore, it becomes an easy target for trimming, which leaves us electromagnetics educators feel insulted. Right, because when my subject is being pruned or sometimes removed, in many institutions electromagnetics is not even a core course, right? So which is unfortunate. That is how we would say, because that's what we know a little bit, and then we teach. So these are the EM specific challenges. Now there are two ways. So how do we respond to curricular pressures? One is the realization that foundational knowledge is of course important. There is no doubt about that. But so also is important state of art. So whenever students graduate at the end of 4 years, they ought to have a decent foundation. They also ought to have a decent familiarity and knowledge of state of the art. Therefore, what is required is sort of a give and take. The old sometimes has to give way to accommodate the new. Right. So that is one, I think, aspect that we should have in mind. Another thing is that, some students go for higher studies, some students may go for industries, and these may present competing requirements. For example, higher studies usually require mathematical rigor, whereas industries may not need that much rigor. So we have to obviously cater to both the requirements, because we never know where our students, especially electromagnetics is offered in second year. So we have to try to accommodate, both requirements. That is also a challenge. So this all calls for a more efficient coverage of the course material, which is a challenge. Okay, I do not have any ready-made solutions to offer, but some approaches that can be suggested are like integration of engineering electromagnetics with the physics course that we offer in the first year. So, of course, this would call for a better coordination to be established between physics teachers, mathematics teachers, and EM and antennas teachers, so that we can more efficiently cover. This may be one way. Another way is the first year PG courses can be used to mitigate, to sort of to bridge the gap that the students may have. First year PG courses in communication or microwave engineering, we should be able to find some space, but again, there also a similar pressures would be there. So anyway, these are some possibilities that we can consider. So having said that, what is the approach? Because we have said learning is challenging. Therefore, teacher's role becomes very central. So what are the approaches? So addressing curriculum is one aspect. Another thing is, how can we address the learning challenges through teaching approaches? So some thoughts. First and foremost, I believe, is the teacher enthusiasm. In my opinion, it is not about techniques, it is not about simulation, animation, anything. So when the teacher enters into the class, can the student see him or her as a bundle of energy, very keen to teach the subject? I think that can make a big difference. Right? When the teacher is enthusiastically expressing some concept or ideas, so obviously that will have a better impact. So in my opinion, the first thing is teacher enthusiasm. There is no replacement. Of course, there are many techniques also, some of which I will just briefly say, and focus on conceptual clarity. When we talk of conceptual clarity, it is not something I read a book and then develop. In my experience, it comes over a period of time, and then it of course continues to be refined also, especially in a subject like electromagnetics, which is whose beauty comes from the space it provides for interpretation. Right? If we take continuity equation or antenna gain, anything, many things. So the conceptual clarity, the teacher has to be a continuous learner, of course, right? We always admit that a teacher is a learner also. Then only he or she can try to be a, reasonably okay-ish teacher kind of, right? So this conceptual clarity is not something, attend a course, you develop it. No, I don't think that works like that. It depends. It requires me as a teacher to continually read, more importantly, reflect and contemplate and discuss with the peers, meeting in conferences or in any forum. So all these, if you take continuity equation or law of conservation of charge and all that, so many Maxwell's equations, displacement current, extraordinary ideas that requires conceptual clarity to be continually built and refined. That is one thing I believe. And here, use of own illustrations to simple things, simple sketches, not because I am more a PowerPoint teacher, so I'm talking of illustrations, preparing some drawings and all, as I will be just demonstrating to some extent as we move on. And then use of MATLAB course when the students develop that themselves. And towards the end of this talk, there is going to be a demonstration by my research scholar, Ms. M. Akila, who will be demonstrating some of the MATLAB codes that she has developed and which we have used in our master's class just this semester. So students really enjoyed that. Of course, she will be sharing that experience briefly towards the end. And of course, this list I am trying to present in the order in which I consider them to be important. So the first thing, as I said, teacher enthusiasm. Even if nothing else is there, I believe that is the first thing. Second is focus on conceptual clarity. That adds beauty to what we teach, and for our own interpretation, contemplation, and there to take the concepts across better, our own illustrations, making simple sketches. Okay, that can be effective. And then MATLAB codes, guiding students to write MATLAB codes after an idea is taught in the class, and then when they see that, it can have a very good impact. Or if it is not possible, use of available codes and animations from the internet. That also, in fact, one of the codes Akila will be demonstrating is online code also. And animations, I am using animations in my class. Some of that I will be sharing as we move on. Then this can be student presentations. Usually students, like to be given responsibility. See, all of us want space, right? All of us want freedom. So when students are given some topic and then asked to present, and when some weight is also given, 5%, 10% and all, the enthusiasm students will show, that is very commendable. Right, so student presentations can be very good. Of course I try this, especially, of course I should say, in the management class, ethics class and all. These can be very powerful also in of course subjects like electromagnetics. And of course the last thing is experimental demonstration. So you can just look at this web link website, which gives some experiments that can be built for classroom demonstration. So these are all some of the approach. As I told, these are in the order in which I believe the order of importance, I believe. So with this, we will just move on to sharing some ideas on how do I try to teach electromagnetics. As I said, these are not necessarily the best ways, or these are not necessarily the only ways, obviously. And some of you might be doing far better than this, but this is now based on just my, the way I just try to teach. So one challenge that I believe students are likely to have in electromagnetics is the maze of equations. Large number of equations, is it not? Coulomb's law, Gauss law, Laplace equation, Poisson's equation, continuity equation, then magnetic vector potential, electric vector potential, scalar potential, too many equations. So I think it's very important for the broad picture of electromagnetics too. In fact, for any life itself, generally the broad picture. And then when I'm able to place the specifics into the context of the broad picture, then things seem to make better sense. So I think the one of the things I always do, this is one of the first things I do in antenna engineering class or signal integrity class also. I believe, I don't remember exactly. Okay. So what is the big picture I refer to? So most of the electromagnetic problems are to do with determining, starting from sources. Sources are in general electric charge density rho and electric conduction density J. And of course, we also add magnetic charge rho m and magnetic current density, especially when we discuss aperture antennas. So, okay, so sources, these are the sources. From the sources, I want to determine fields, E and B. Okay, this is like in circuits, students may not have that much difficulty because they know, okay, what is very often required is voltage and current. And in electromagnetics, it is just analogous to that. Very often what I need is the fields E and B, which are just analogous to V and I in circuits. So in some cases, I can directly start from sources and determine fields. Often it is the case that this mathematics becomes too complicated. Therefore, we introduce auxiliary potentials or secondary potentials called A and F, or magnetic vector potential and electric vector potential. So determine the potentials from sources and determines the fields from potentials. This can, for aperture antenna analysis, for linear wire antenna analysis also, this is how we do, if you just recollect, because this makes the mathematics simpler. So once I have the fields E and B, I can determine the parameters of final interest, which can be power density, directivity, or power absorbed in a microwave oven and things like that. So this is the broad picture in most of the problems. And obviously this needs equations that relate fields to sources often via potentials. So like Coulomb's law, what does it give us? It gives us fields, right? So I can employ Coulomb's law to determine electric fields. Similarly, Gauss law also is an equation that helps me with determining electric field. Similarly, Ampere's law and all that. Through potentials, Laplace equation also. Laplace equation, I can determine V, and then once I know V, I can determine E through that equation. So we need equations that relate sources to fields, often via potentials, and parameters to fields. So once I have the E and B, how do I determine my power density, that Poynting vector and all that. So this, I think, is a broad picture. Most of the equations, I believe, can be put into one of these boxes. So if this broad picture is clear, it is probable that students will have slightly less difficulty in placing the many equations in context. So this is one thing that I believe is important. And then now what I'm going to do is to take any number of topics, discrete topics, not necessarily related, and then to just discuss how I try to present that in the class. So many could be disjointed, except that they're all electromagnetic equations or concepts. Apart from that, nothing necessarily links the many topics we are going to discuss from now on. So Gauss law. Okay, so Gauss law, obviously the primary concept the students have to understand is flux. So how I discuss flux is, are you able to see my hand and what I'm showing now? A sheet of paper?
Yes, we are able to see.
Yeah, thank you. So, so what is flux? How is it different from field? Okay. So how I discuss this in this class, let us say there is a flow of some fields.
Just one moment, Professor Selvan. I just wanted to tell the participants, if they want to see you, they can pin on your video clip so that you will come full screen to them. It's up to them to pin or unpin, depending on whether they want to see you or the slide.
Yeah, sure.
Yeah, I'm hoping that they...
So can I proceed?
Yes, please.
Yeah. So I have a sheet of paper which represents a surface. Okay, this is a surface for us. A surface, of course, in electromagnetics, we define a normal. The surface as a normal. Let us say it is directed like this. Now, there is a field. It can be electric field, magnetic field, or just any field that is flowing, air fields, air, or just any velocity, some fluid, it is flowing. Now, the fluid's velocity is also directed like this. It goes through this surface, comes out. Now, the surface normal and the flow direction, they coincide. Is it not? Surface normal is directed like this, and the flow is also directed like this. So the angle between them is 0. Obviously, we know that there is a maximum flow through the surface. Of course, this becomes even more comprehensible when I just turn, keeping the fluid direction, the fluid movement direction is same. It does not change, but I'm just turning my surface like this, slowly turning and making it perpendicular now. So the surface normal in this case is now towards me, whereas fluid is like this. So there is a perpendicular 90 degree between the fluid direction and the surface normal. In this case, is there a field flowing through the surface? No, right? It is 0, correct? There is no, because it just has become perpendicular to this. Now, this is what we mean by flux. What is flux? Flow of fields through a surface. So how flux is different from field? Flux is fields, but flow of field through a surface. So the illustrations, this is how I explain in the class. And of course, these pictures are from Halliday and Resnick. We can draw our own pictures. I mean, simple sketches here. So now I recognize now in discussing this, that it's a dot product. The flux is, in this case, for example, V dot A. Because 0 degree and then it becomes 90 degree maximum flux to 0 flux, like that, right? So it can be E dot A, right? So flux. So when we discuss Gauss law, the first idea to be discussed is flux. Once I introduce flux, then it becomes much easier to discuss Gauss law. We consider a surface. Again, we have defined here, this is a differential area dA, and the normal is directed like this. Let us say the electric field. So there is an electric field directed at an angle theta. Now, what Gauss law tells me is that if I integrate the electric field throughout the surface, that gives me the charge enclosed by the surface. Okay, I think this way, when we present Gauss law, it probably will reach better. And when we discuss applications of Gauss law, we say normally that in symmetry situations, Gauss law simplifies field estimation very significantly. There's a very interesting animation which I'm going to show. I'm sure you'll be able to see. And this website, please note down this website. This contains a lot of interesting animations that can be used in the class. I'm just clicking this. Please closely watch this. Axial symmetry. This for a line charge, how Gauss law can be used to estimate. So these surfaces that the caps, they are perpendicular to the normal is perpendicular to the field flow. Therefore there is no flux. So that's all. So it is very quick, but you can stop anywhere and watch this and then discuss with students. Like this, you can just pause it and then see. Just one more time I will play and then move on to the next. Yeah. Okay. So this is one topic. Next, we will take electric potential. Potential is a extraordinarily important thing, right? Potential is the mover of things. Everything, energy is potential. So how I been trying to discuss this in this class. It's a very interesting idea. I mean, so physics, I mean, electromagnetics is, heavily physics, oriented. So what I do, okay, I move a mass, some object from the table to a certain height. Now, this stores energy. How do I know? If I just drop it, either it can break or if I drop it on my palm, it paints, right? So it paints because of the energy that is transmitted to my palm, right? So this stores some energy now. So how is it that this has acquired energy? So how do we conceptualize this? It is able to store this energy because I have moved this object, some external, I am an external agency here. I have moved this object against gravity. So in this process, I have done work, and that work is stored as energy in this object. So this is in the context of gravitational potential and gravitational energy. So this is, I think students will be able to connect this better. Now, what is potential in electrical context? Very similar thing. We will again go to an animation. So in electricity, we have two charges, like charges repel and unlike charges attract. So let us look at this animation. Yeah, okay. So these are two positive charges. So now positive charges, they are like charges, they repel. So the closer they are, the more energy. The distinction between gravitational potential and gravitational energy and the electric energy is, in electricity we have two kinds of charges. Whereas in gravity, there is only one, right? It's only attractive. But here, it is both attractive and repulsive. So that makes it even more interesting in this case. So now I can just, both are positive charges. The closer the charges are, the more is the potential energy. That's easy to connect, right? The farther they are, the less is the potential energy. You can just move this. Now I'm going to move. Please watch the curve. See, we can see increasing energy. U is potential energy, how it increases like that, right? So exponential increase because of the charges coming closer. And if I go to a negative charge, now in this case, they attract each other. So the farther they are, the more is the energy. So now when I bring it closer, energy, energy declines like this. Okay, so this idea, now, okay, where is that? Now, after discussing this, if we get to this simple illustration, so an electric field is directed like this. I am moving a positive charge. So who is moving? A third party, like I lifted the object, right, from the table. So I'm moving a positive charge against this field. Therefore, I have to do work. And now work is force into distance, and force is QE, and into distance dot, it is also a dot product because it depends, obviously. I mean, that's a simple thing. Now this minus sign becomes, I mean, it is important because I am moving against the field. But when I do this, in this case, a positive charge, dW, when I calculate differential work done, it is a positive charge I'm moving in this case. In this case, I'm moving a positive charge, so minus sign comes from the equation, minus plus Q, E dl. E is electric field, dl is the displacement through which I'm moving, cos 180. Cos 180 is minus 1. Therefore, the differential work done is positive. Okay, so this negative sign is required to ensure the correct sign. Of course, positive sign, negative sign is because, conceptually, because we are working against the field, therefore we add. So once this idea is clear, then it is, differential potential is defined as differential work done per charge, which is dot E dot dl. And then it can also be generalized to three-dimensional, that gradient equation, E is equal to minus del V, that can be developed from this. So this is potential. And then drift velocity. Again, please don't get confused. As I said, I'm just, picking several topics. The idea is, is how we can sprinkle, being our interaction in 1 hour, 1.5 hours interaction, how much we can, cherish teaching different ideas. You can, of course, use that. Each of you would have your own favorite concepts, right? So that you can explore, and then always there is, once you have the interest and all, it's always possible to find out resources and then contemplate and come up with interesting ideas of teaching. So first thing, we start with this. Let us consider the case of a specific case of a 1 millimeter diameter copper wire carrying some current. I have taken this example from somewhere. That's why this odd number, okay? Not exactly odd, 1.67 ampere current. The drift velocity for this situation is 1.5 into 10 power minus 4 meter per second, okay? Now, see, copper is the usual for electric wires and all we are using. So if the drift velocity is so low, then does it mean that when I switch on, for example, in this room, I'm sitting in this room, let us say my fan is some 3 meters away from the switch. So is the electron going to take that much time as determined by drift velocity? No, right? No, that's an interesting question to discuss with the class. That is because the energy transfer, because when we apply a voltage, we are giving an electric field. That electric field propagation is instantaneous. So if this is my copper wire, everywhere that drifting takes place. The way it takes place here, it takes place all along, and here also at the same, almost at the same instant. So that is why it is instantaneous. This animation is very interesting. As we know, in any conductor, this is random walk. In any conductor, electrons are in random motion. Now, you see, please carefully see, initially, the part showed electrons in random motion, and how the application of an electric field, I just run it again, electric field makes it more sort of oriented. Now, unless you are able to keenly watch, not to worry. I mean, if within the time, if you are not able to watch, you can always carefully you can do at home and then watch this. So this is again, I think this is the site I already showed. Very, very nice site, having a lot of interesting animations. Then, as I said, continuity equation. So continuity equation has to be linked to law of conservation of energy. So what is continuity equation? Let us say there is a current flow, there is a volume, there is a closed volume, there is a flow of current through that surface, through that volume. Okay, so if there is a flow, it has to be necessarily associated with the declining charge density within this volume, right? So immediately that should take us to the idea of law of conservation of charge, where charge can neither be created nor destroyed, okay? It can only be transferred from one place to another. And also law of conservation of energy. Energy can neither be created nor destroyed. So continuity equation, which is a very fundamental equation in electromagnetics, that is actually related to conservation of energy and conservation of charge. Ideas such as this can be of interest to at least some students. Then the next is boundary condition. Boundary conditions. So PEC, we consider a perfect electric conductor. We know the tangential electric field is 0. it is possible to discuss conceptually as to why this is 0 by a simple illustration. Let us say, as the counter argument, that there is an electric field which is tangential to a PEC. But if such a field has to exist, then I should necessarily have a charge distribution like this, is it not? Plus minus, then only the field will be directed like this. So if there is a tangential field appearing like this, and then this charge distribution will induce also a redistribution or reorientation within the PEC, which is like this, because this will attract negative charges, this. So this will produce a counter field resulting in cancellation of the fields. So this is one way we can try to discuss as to why the tangential electric field at the surface of a PEC is 0. But the implications of this tangential field being 0 in antenna engineering or artificial magnetic conductors is very, very interesting. So when we build that idea starting from here, then it probably will make things more interesting. So now one immediate implication of this tangential field being 0 at the surface of PEC is that the phase of the reflected wave has to be reversed. Why it has to be reversed? Let us consider this, an electric field is incident like this. Now we have said, so it just comes here. So if I have to have a 0 tangential field at the surface, the field has to necessarily reverse, right? Reverse. Then only I will have a 0 field here. So phase reversal. Now, this phase reversal has implication in antenna design, because if my ground plane is very close to the antenna, a ground plane is a PEC, typically PEC. A ground plane, if it reverses the phase of the wave, then there is going to be destructive interference ahead of the antenna. That will lead to reduced gain, is it not? So how I can circumvent this is I enlarge the separation. I make it lambda by 4 at least at the design frequency. So which means each lambda by 4 gives 90 degree, lambda by 4 corresponds to 90 degree phase shift, 90 degree, another 90 degree, there is already 180, therefore 360. So which means the two waves arriving here or in phase, they lead to constructive interference. But the problem here is now, miniaturization is becoming very prominent. And therefore, this will present challenges to miniaturization. So how do we sort of address that is by, by using AMC, artificial magnetic conductor. So before that, let us just look at the surface impedance. We say surface impedance is a low impedance surface. A low impedance surface is a PEC. Why do we say that? Is because of this. Let us consider a PEC lying on YZ surface, propagation vector, an electromagnetic wave is incident. So the surface impedance is defined as electric field, surface electric field divided by HY, EZ, HY. EZ is 0. Therefore, ZS is 0. So 0 for a perfect electric conductor. For a good conductor, therefore, it is low. It's not 0, okay, because it has certain resistivity. Therefore, for a good conductor, the surface impedance is low. That is why we say. So whereas the artificial magnetic conductor, which are periodic structures, they are complement to PEC, which means the tangential magnetic field rather than electric field is at 0 at those surfaces, and therefore naturally they are called also high impedance surfaces, and they reflect electric field without phase reversal. So such surfaces can be placed very close to the antenna without affecting, without resulting in the kind of problem we would have when I use PEC. Next is Faraday's law. So I hope these jumps, I'm jumping from one topic to the other. So the idea is, to have, I believe that most of the attendees are young faculty. That's the belief, but even, age is just a number, right? So we can always find, personally, this is how I try to take my teaching. Unless I enjoy, how is it possible for students to enjoy? Is it not? So if I go into the class with a very bored face, with unenthusiastic face, obviously, that is a contagious thing. So enthusiasm, at the end, we'll just discuss a bit about that. It's very difficult. How do we remain enthusiastic in conditions that such as what we have? So Faraday's law, again, a nice simulation from Colorado State University. It's simple, very simple. We can also, I mean, with interested UG students, I think our people also can make simulations like this, animations. Very simple. So a bulb. Now, so you can see at the below voltmeter and field lines. I'm clicking both because I want to see how a voltmeter needle just goes when I. So Faraday's law, of course, a changing magnetic field produces an electric field, or when a changing magnetic flux linking a suitably closed surface produces a voltage, right? So this is the magnetic field source. This is the source of magnetic field. Right now also there is a linking of this field, but that is not changing. So law says changing magnetic flux. So now what I do, I'm just changing. I can see the needle oscillating. Now when I see now when the substantial change, then the bulb glows. So this is fun. There's a little bit of this adds spice to, and not only spice. I think this will make the concept clearer to students. And of course, the teacher, the classroom should have internet connectivity. That is important. Then the teacher can use. And then I mentioned that student presentation activities especially can be very useful, because students when they are given responsibility and some mark also right, some reward is expected, then electric guitar and magnetic levitation trains, for example. See, these are suggested topics. There are many number of topics, right? So we can just assign a topic, or we can encourage students to come up with their own topic. Okay, make it 10 minutes, 15 minutes, a group presentation employing on an application that makes use of Faraday's law. In your presentation, explain how Faraday's law actually forms the core foundation of that application. Like that, for example, you assign some 10 marks or something. But again, I'm aware many of the colleagues can be from affiliated colleges, which may not have space, is practically nil. But anyway, those are things that the new education policy and other things, hopefully things will change in the future. But within this space, but all of us, nobody can deny that there is some space available to all of us. Our colleagues in IIT, they have a lot of space probably, but I have less, someone has less. But some space is available. So we have to, it is in our hands to make the as best use of the space that we have. So presentations can be very helpful. Then the antenna directivity. So until now, I mean, I just pause here and then take any comments or criticisms or questions.
Any questions from the participants?
My request to participants is that if they can identify this while teaching a certain concept, this is a good time for discussing those. I'm sure many of you will be having similar difficulties in certain concepts. So it will be very good if somebody from the participant group start this discussion.
Professor, I have a fundamental question.
Yeah.
So nowadays, people are thinking that we have to directly go for application, and teaching of basics is not needed. So what is your comment on that? Should we teach basics and then we have to go for application, or that directly we can go for application?
Yeah, it's a very interesting question, vexed question also, because I am also aware of such. Anyway, at the end, I have some comments to make on this also. But now, see, there is a colleague in Intel who is other industry friends. If we really look at, I mean, excellent industry engineers in antenna field or any electromagnetics or anywhere, they do not agree that theoretical foundation is not necessary. So that is one aspect. Then how I like my own PhD scholars to develop, how it is my personal opinion that unless a person has a reasonable grasp of fundamental ideas, it may be difficult to be a very good application engineer also. I mean, this is again, whether this is a biased opinion, I'm not sure about it. But it is, I mean, how do I understand? For example, now, as I'm sure all of us are aware, simulation, extensive use of simulation tool is made for by PhD students. That's okay, but then there is also concern about the students often failing to understand how to interpret results or what probably causes the mismatch and things like that. So without a reasonable grasp of foundation, I can't understand as to how one can sort of innovate very successfully over a period of time. So I believe that fundamentals are very, very important. I think that's what I'm able to say. So I hope the questionnaire. Anyway, these are all things for continuous reflection. There are no definitive and finalistic answers to solve our problems. These are academic issues that require continuous reflection. Thank you for that. A very nice interaction. We will move on. The next thing is antenna directivity. So antenna directivity, like in the class, if you say, this is from Balanis, this definition, ratio of radiation intensity in a given direction to that of an isotropic source. This is not very easy for students to connect. For me also, I mean, even, right? So here, as I said, illustration, simple illustration. So, and then one thing is, see, I have been in academics for 15 years. Okay, 2005, 16 years now. Yeah, 16 years. But not that I started teaching antenna directivity this way from the start itself. Probably in the last couple of years or 2-3 years. That is what I meant by continuous learning and continuous contemplation on the part of the teacher as to how I can, because very often we would say we would leave a class being dissatisfied. Oh, today I think I didn't do a neat job. We will know, right? More than anyone else, we will know. So how can I present that better? And this may or may not be possible for all the topics. So wherever it is possible. And one important thing here, how do students, how do students learn, or how do students view a teacher? Not from how a teacher conducts or teaches every moment that he or she is in the class, but some highlights. If a teacher is able to make an impact in one particular, or say out of 100 topics you teach, for example, you really make a difference with a 10 or 20, because preparing such illustrations or contemplating also takes time and energy, right? So that itself can make a big difference. So if you can just focus on 2, 3, 4, gradually we build that repository. Over a period of time we have better illustrations, right? So antenna directivity, how I try to teach in the last few years is, okay, this is PR. I'm inputting a certain power into an antenna, which is for now it is an isotropic source. If it is an isotropic source, it distributes power uniformly. Of course, let us visualize this in 3 dimensions, though it is a 2-dimensional sketch. Now, instead of, rather than being an isotropic source, if it is a practical antenna, which is a directional antenna, the distribution of power will be like this. Now, let us consider an arbitrary direction like this. So at this point, this is radiation intensity due to isotropic source, and radiation intensity due to this directional source. Now I define the directivity in this direction. Directivity is a directional property. Therefore, radiation intensity due to that and divided by radiation intensity due to the isotropic source. But normally by antenna directivity, we refer to the maximum directivity, which is usually along the axis of the radiation. So in this case, okay, here I have U0. U0 remains. U0 doesn't change, but maximum directivity, I can, maximum directivity is defined as maximum radiation intensity due to the antenna divided by isotropic. And I'm sure there is scope for improving this, illustration. There is always a scope for improving antenna directivity, polarization. And this is always reminds me when I attended Samir interview, late Professor Narasimhan, IIT Madras. He was a committee member. Actually, I had met him as a third year or fourth year UG student. I had met him in the campus, 87 or 88 or around that time. Because of my interest, I was interested in electromagnetics in UG days. In fact, in third year, when I was in third year, my classmates asked me to explain Gauss law, which I did. I remember on a board, how well I did, I'm sure I would not have done very well and all, as if I'm doing very well now. Anyway, so Professor Narasimhan, I had met him with my interest. So at the interview, he asked me a question on polarization. That is how my memory goes. Polarization, and my memory is also that I did not give a very nice answer. Because it is a somewhat difficult concept for students, for us also. So how I try to teach in the recent years. So E is a vector. See, it is important to remind students that E and H are vectors. So they have a direction and magnitude, okay? Not only the first topic as vectors and all, subsequently also from time to time. So E is a vector and therefore is H. And in the far field, when uniform plane wave conditions exist, we say E and H are perpendicular to each other. Therefore, if I know one, then I can set the direction of other. That is why we just normally we refer to the direction of E as the polarization. So in this case, the wave propagation is into the page by right hand rule, E cross H into the page. So E is like this. Now let us say E becomes like this, then H also becomes like this. So this is the first idea that the student should know. So they are perpendicular to each other. Now, let us consider that in general, E can be directed arbitrarily, randomly like this. So, which means E has, it can be decomposed into two components, namely X and Y components. Isn't it? So now we can say, okay, before that, E can be expressed as the sum of, this is in phasor domain, X component and Y component. Propagation is along, positive is a direction. So this is in general. So now I can define linear polarization. If this E is linearly polarized in X, if X component is 1 and Y component, there is no Y component, only X component. Or similarly, only Y component, there is no X component, then it is Y polarized. And similarly, it is polarized in 45-degree direction when the X and Y components have equal magnitude and so on. So this is linear polarization. Now, I think what is important to emphasize that E in general can be decomposed into two components. This understanding can lead us to the next step, which is that the two components, it is possible for the two components to have a phase difference. Okay, so one component starting earlier or later than the other. So first thing is components. Components we introduce by arbitrarily orienting the electric field, then X and Y components. There can be introduced a phase shift between them. Now what happens? Now, of course, this I am just looking at the real domain in time domain. So real part of AX plus JY, we know plus J corresponds to 90 degree. So I have introduced a phase shift of 90 degree between the two components, X and Y components. And I am looking at the time domain. I can simplify this to this. So if we plot this, then either as a function of, for a given Z as a function of t, or for a given t as a function of Z, we will be able to understand the circular and linear polarization. There are going to be two animations. One I am going to show now, and the other Kila towards the end, she will be demonstrating another. And when it comes to the left-hand circular polarization and right-hand circular polarization, that is that we always know we have to refer to the, it has to be with reference to either the source or receiver. Because now if I say, to me, this is clockwise, but to you, this will be anti-clockwise. Therefore, when I say it is left-hand circularly polarized, then I should say with reference to what I'm mentioning that. So we will look at a very interesting animation. So when X and Y components have 90° and they are equal magnitude, when we get circular polarization. When the phase difference is not exactly 90° or the amplitudes are different, then we get elliptical polarization. So please watch this YouTube video very carefully, very interesting animation. Watch carefully. Now this is linear polarization. Be prepared. There is going to be a phase shift introduced now. Now, both red and blue are E field lines. Yeah, phase shift. Yeah, that's it. So enjoy this at home. I'm sure the recording will be available to you. Therefore, I don't know how. So you can note down this this link. It's very, very helpful. Okay. So we will move on. Array antenna concepts. On this also, there will be a MATLAB code-based demonstration at the end. So how I try to teach this? Again, simple sketches made by the instructor. Simple sketches, okay? So two isotropic sources. First, we consider identical amplitude. Two isotropic sources, identical amplitude and phase currents. They are spaced lambda by 2 apart. So this is my coordinate system. I place the two isotropic sources along Z axis. They are both fed in phase with identical amplitude. Okay. So the spacing is lambda by 2. So as we mentioned earlier, lambda by 2 corresponds to 180-degree phase shift, is it not? Is it not? Lambda is 2 pi radian. So one complete transformation. So lambda by 2 corresponds to 180-degree phase shift. Therefore, when in this direction, if I look at, first on the top, if I look at these waves will arrive in phase. Therefore, there is addition. The strength doubles. And similarly, it happens below also. Whereas if we consider either to the right or the left, let us first consider to the right. What happens is, because of this lambda by 2, there is an additional, there is a phase, there is a reversal of phase, because 180-degree. So by the time the energy leaving from this reaches this, it has undergone a phase reversal. Therefore, the waves here cancel. And similarly, it happens to the to the left also. Now I can write, I can just sketch this, and then the equation also can be written, because this, if you plot, you please see that cos pi by 2 cos theta. So if we plot this, we will get this. So here I have a maximum along x and minimum along y. Maximum along x, minimum along y. So now, this is a case where two isotropic sources place lambda by 2 fed with identical magnitudes. Now, what I'm going to do same, everything is same, except that I'm introducing a phase shift. So one of the elements is fed with opposite phase. Okay, opposite phase. So that means 180 phase shift. Now I am just going to run through. You will understand for yourself. Here in this direction, waves will add, because now when the signal from this reaches this point, already it has undergone 180-degree phase shift. This already is an inbuilt 180-degree phase shift. Therefore, they add. And similarly, this side, whereas they cancel above and below. So which means gradation pattern. Here I have maximum along Z and minimum along X. Now, of course, I can extend this to n number of elements. And more importantly, the clue to phased array comes from here. So though I have retained everything, just by changing the phase shift between the elements, I have been able to reorient the direction of maximum. Is it not? That is phased array. Phased array where we change the phase between the elements and phase shift between the elements. We can steer the beam like that. But the fundamental ideas actually derive from these simple cases. Therefore, this and then writing a MATLAB code extending to n elements and all can be very helpful. So with that, and then this is we have few more things. I will take another 10 minutes and then try to wind up what I have. Then Akila will take over for her demonstration. This dielectric polarization, this is the idea I somehow like. As I said, see, though the whole subject, some of the parts may be interesting because all of us are human beings. So we will have, the preferences also. That's fine. So whichever topic excites you, there we can just, try to introduce depth in the class. So we become enriched. Oh, wow, my understanding improves. So my confidence as a teacher improves. Then my students, hopefully, their learning improves. So that's, like that. So polarization, very, very important, especially now, modern times, research students, most of them work on printed antennas. So understanding the substrate behavior is very, very critical to understanding. Sometimes we're discussing about simulation results and, and all that. To make sense of simulation results, a good understanding of also of substrate properties is very important. So we have an atom. This is not excited, so which means it's a neutral atom. I have a nucleus and the electron cloud. The center of the electron cloud and the nucleus, they coincide. Okay, so that is electrically neutral. So there is no external electric field in this case. Now, when I excite this atom with an external electric field, what happens? There is a shifting of charges. Right, electric field is directed like this, therefore positive charge goes like that. The electron cloud shifts here, so which means there is a net positive charge net. Earlier in this case A, we said the centers of nucleus and the electron cloud coincides, but that's not the case in this case, where it has become a stretched spring because plus has been moved up. The electron cloud has been moved down. So it becomes a stretched spring. Therefore, this can store energy. Is it not? So this is the fundamental idea of dielectrics, dielectric polarization, a capacitor. It's also like, if you see, this is actually a capacitor, right? So I have a positive charged plate and a negatively charged plate and all. So this is the atomic level understanding. I can, very, very interesting animation, but yeah. So I think, okay. So let us move down. Okay. So this is the red thing is the electron cloud. Okay. This is nucleus and field is alternating. So it is polarization shifts. Now another animation I would show, but in the interest of time, I'm just going to tell something here. Now, when I increase the frequency of this oscillation, what will happen? The polarization also has to keep pace, right? Isn't it? So when my frequency 1 gigahertz, 2, 3, 10 gigahertz, then the polarization also has to keep pace. But whereas this is an electrical change, therefore it can take place instantaneously. But whereas this is, in our conception, this is a mechanical thing, right? So atoms reorienting, molecules reorienting themselves, that is a mechanical thing. So which cannot keep pace with the changing electric fields. So that will introduce frictional losses. So when we increase the frequency of operation, like substrates display, not only substrates, metals also display changing material properties as a function of frequency. This is a very, very important idea. Actually, wideband antennas, when you are signal integrity ideas there, as we will be just briefly mentioning. So this animation is interesting. Okay. So now I can just consider a macroscopic dielectric. When an electric field is applied, there is a net accumulation of positive charge on the top, net accumulation of negative charge here. This results in an internal electric field, isn't it? Internal electric field. This internal electric field obviously changes the net field within the dielectric. And this change does not occur only inside the dielectric, but in principle also outside the dielectric. Why? Because see, when this is the original external electric fields. Now, when I have polarization induced like this, there is going to be an external field like capacitor fringe fields. I'm also going to have an electric field here, right? So when a dielectric is placed, it is going to impact fields both inside as well as outside of the dielectric. Probably the impact outside may not be significant, but not to say that it will not exist at all. So with this idea, now we can introduce the equation. So now the electric flux density D, now this E, see, if all that we had was free space electromagnetics, E and B would have been enough. But D and H became necessary or become necessary because we also deal with materials which display their own properties to their own responses to electromagnetic fields. So in the case of dielectric, D is equal to this is in free space plus polarization fields that results in that leads to the introduction of relative permittivity. Okay, and then we already noted this animation. I'm not going to show. You can just watch it later. We already mentioned that. What did we mention? That as the higher the frequency, it is possible that the mechanical reorientation of the molecule cannot keep pace. Therefore, loss tangent, right? Losses within the dielectric and dielectric constant, both real and imaginary part will undergo change. Models, lot of models have been developed for this by modeling this as a simple harmonic motion. In fact, in this animation, that is what you can watch, simple harmonic motion, and then how that has been used to model the frequency dependence of dielectric properties of substrates. And this is very important. Wideband printed antenna design, when you are trying to make sense of the discrepancy between measurement and theory, assuming the measurement and simulation often, even assuming that you have done the simulation well, but still discrepancies are inevitable part of life, right? So how do we account for that? There things like this can be used. Signal integrity also, as I will be very briefly noting. 5 more minutes I have, and this is an interesting measurement. Which actually these measurements were done in Professor Subramanian's lab some time back, I think last year or so. Let me skip this because there are this is interesting, but a lot of things are interesting as well. Then antenna measurement challenges. Very briefly, this measurement, measurement is an extremely interesting topic by itself. It can be great fun. I mean, when I was in Samir, actually, I so passionately built this, what I call birail test range. It was quite nice. So this is on the terrace of Samir, Chennai. So enjoying some good publications came out of measurements, some transactions and other journals. Very enjoyable. I always used to enjoy, being on terrace, sometimes having a cup of tea and undertaking measurements. Very nice. So measurements is, I think we should encourage students. Measurement is not simply connecting and taking reading. It is much more than that. Especially wireless measurements are a lot more demanding and challenging. So here, of course, we talk of proximity effect, and proximity effect is different from multipath interference. A proximity effect comes because of our having near field and far field. So in 2017, Professor Ramakrishna Janaswamy and myself wrote a paper in IEEE Antennas and Propagation magazine, which presents a unified derivation for aperture antennas, that a near field and far field 2D square by lambda. And similarly, there is one which I don't remember for near field, right? So that presents a unified derivation. So multipath interference is different from this. So these ideas, usually when we carry out measurements, we want the test antenna to be illuminated by my transmitting antenna alone. But that is not how it will happen. There will be, the array will also be incident, energy will also be incident on the floor and then reflected and impinge and interfere with your test antenna. Not only this, because usually let us consider a room in which measurement is done, there are going to be reflections from all sides. So what we do, that is why we introduce RF absorbers, which can attenuate whatever is incident, resulting in my test antenna being illuminated essentially by the signal from this transmitting antenna. So this idea, and particular care has to be taken for low profile antennas. If you just think of that, low profile antennas, low gain antennas, so they have to be necessarily omnidirectional, broad beam. So that beam will illuminate all nooks and corners of the chamber. Therefore, reflections are going to be more. So measurement of low profile antennas is particularly difficult. Antenna alignment, I just skip. And coming to high speed digital design is very, very interesting. Animation, I'm going to skip. This, we know that any digital pulse contains a large number of, by Fourier transform, it can be decomposed into a large number of or infinite number of sinusoidal signals. A very simple illustration now. See, very crude approximation of a square pulse. Even one sinusoidal signal, see, like if we look at this is a very crude approximation of a digital pulse, right? But then when I want to better my approximation, I increase the number of terms, 2 terms, 3 terms, and then Professor Subramanian, can I take just 5 minutes more than the allocated time?
Yeah, no problem, no problem. Please.
No problem. I am very worried because the audience should not feel, so please allow me to take just 5 more minutes, because Akhilas also follow. So in 5 more minutes, I will close. Let us look at this animation. This would be the last animation, okay? Okay. Oh, I'm sorry. I think I'm sorry. That is oh, still this is there. What's happening? Let me close this. I think this is why I'm not able to go back. Oh. So I'm sorry about the interruption. Is the presentation visible now? Is the presentation visible now?
Yeah, visible,
right now.
But the only thing is, it is not in the full screen mode.
And then now I will just go to the full screen mode. High speed digital design. Oh yeah. I'm sorry, I did not click the right link.
It is in the bottom one.
Oh. Yeah, correct. YouTube. Carefully watch. Yeah, I'm sure we will be able to extrapolate how a near square pulse can be arrived at by including very large number of sinusoidal signals. No, this presents, we know that a square pulse, an ideal square pulse cannot be produced because no physical system can be in simultaneously two states at the same time, like on and off. Therefore, trapezoidal pulse is very close to the practical pulses that we use. So it is not difficult to see that the bandwidth of a trapezoidal pulse is narrower than that of a square pulse. is it not? A square pulse requires infinite number of frequencies. A trapezoidal pulse requires less. When we consider the Fourier transform on the right, we can see that no. So trapezoidal pulse, all trapezoidal pulses are not same because rise and fall time. So the shorter the rise time, the quicker the pulse rises. In high speed signal, that is what we need. We want our signal to, quick zap to the peak. So then the quicker the rise time and fall time, the larger is the bandwidth. That's not the end. The larger the bandwidth, the larger the number of, assuming that you have 0 to 10 gigahertz, though if let us say you use a 2 gigahertz signal or 5 megahertz signal, digital signal, that can have frequency components that go up to 10 gigahertz or so, significantly, right? So that means that much variation, that we mentioned that material properties are frequency dependent. So we will have to address, that much the impact can have. So resulting high speed challenges or can be significant delay, skin depth, and therefore attenuation and crosstalk, all this. So signal integrity is a very, very interesting and important topic. So with that, we just come to reflections. So what do we draw from all this? So why do we teach? Why do we teach? I think this is an important question. I am an electromagnetic teacher or management teacher or a signal processing teacher. But why do we teach? What are universities for? Okay, we will answer that question. Now, our graduates have to operate effectively over their lifetime, 30 years, 40 years, 50 years, right? Young people, when they graduate, now, so they should be, they should develop imbibing the right characteristics. So are those characteristics only being able to solve problems? Definitely not. Or being able to animate and simulate, right? It's life, right? So it has more. So education fundamentally has more beautiful, more far-reaching objectives than the discipline-specific skills, which are electromagnetics, animation, antennas, and all, which are very important. But through this, can we also, try to share some ideas of the other aspects of life, like openness, lifelong learning. Those things are important. According to the Chicago Handbook for Teachers, a reward of good teaching, a very nice statement. I like this. The knowledge that we have instilled modes of thinking, how to think, right? Created intellectual passion, so that they can pursue whatever they choose to pursue nicely and creatively, promoted forms of tolerance and understanding. So this, I think this is the larger, we can just build upon it and then discuss, why do we teach? Are we teaching to pass exams, to make great designers just alone? No, our objectives. So how does electromagnetic teaching appear in the context of these objectives? Electromagnetics, in my opinion, is a wonderful avenue to facilitate a discussion of many modes of thinking, right? Mode of thinking, like Faraday, Maxwell, terrific. How terrific thinkers, right? So Maxwell's displacement current is something that I have taken as an example. I have tried to teach this in context. Context means not simply Maxwell added dou d by dou t, not like that. Trying to discuss and then teaching in context, how briefly discussing how the idea evolved, and feedback has been reasonably good from conference and classrooms also. So I am, of course, working. I will be working on a talk which will be posted in due course in an IEEE Antennas and Propagation Society Educational Resource Center. I will, of course, let Professor Subramanian know and other audience if I get the contact details. So this earlier, one audience, one colleague asked, do students always link subjects with employment relevance? So now in India, especially large, the most of the employment comes from IT sector. So do we, abolish electromagnetics? No, it doesn't make sense, right? So in my opinion, when the teacher enthusiastically delivers a subject, isn't that students always think in the class, sitting, no, this is not relevant? Or is it possible for us to get them excited by the teacher's involvement, by teacher's energy and enthusiasm? I think this is a question for all of us. And again, an applications only based teaching is not relevant. Because one question I asked myself. So, is it that my students, undergraduates who end up in IT industry, do they have no use of electromagnetics, or can I also find elements in electromagnetics that will help them lifelong in developing other skills like modes of thinking? Electromagnetics is such a fantastic subject to discuss the varied modes of thinking. So, a more holistic approach will be helpful. So, how do we promote electromagnetics education? Faculty development. That is all said and done. It all, I think, significantly boils down to this, and faculty enthusiasm. But again, of course, I am aware of the conditions and all. How do we retain faculty enthusiasm? That is definitely a very important topic for discussion in more appropriate forums. So if we can nourish 100 good faculty, 100, why I like faculty development programs is this. One faculty can, year after year, 10 students, 20 students, right? So faculties or, very teachers or, obviously play a central role in society, and professional societies can play a vital role. Of course, experience, as Professor Subramanian was telling, APS Madras chapter, a lot of programs starting 2013 for many years. This article in February 2021 issue of the magazine, some article, lessons learned from IEEE APS Madras chapter, you can just go through. Then we can also expand the scope of electromagnetics to computer science. Signal integrity and also bioelectromagnetics. This year, myself and my colleague Dr. Esther Florence, we delivered a 1 credit course to on bioelectromagnetics to students from civil, chemical, IT and all. Though only 14 students attended, it was well received, very well received. So we are expanding the scope of electromagnetics. So summary is not exactly ending the talk, because Akila's presentation demonstration also part of my talk, but let me just wind up because it's already time. Importance of adapting to changes in curricular models and student learning styles. So let us all appreciate that the students have a hard time because of the distractions. So we shared some practical ideas. So a teacher to enjoy, he or she has to be a continuous learner, and then continuing to prepare improved teaching material will also, of course, and teacher enthusiasm, there are challenges. Of course, I'm aware because we all are aware, but we have to address how we can improve situations. Some thoughts with that. There are additional resources and a book on electromagnetics teaching edited by myself and Professor Carl Warnick of Brigham Young University, that is in press. That will be June 18th this year, that will be published. So that has 13 multi-institutional, multinational authorship from IIT Madras. Uday Kankoji has contributed to one of the chapters. So 13, very interesting. I hope you will access that book and look at it. And there is this is very important special session on electromagnetics education at IEEE APS International Symposium to be held in Singapore. Please go through this website, and submissions welcome myself, Professor Cynthia Furs, University of Utah, and Carl Warnick. We are organizing a special session on EM education. So contributions are welcome until May, still 2 more months. So please do contribute. And an earlier talk, more or less based on similar ideas, and of course I have made some changes also, is available in an earlier YouTube link. So thank you for the attention. But again, please, this is not the end. So I request Akila to just go through your demonstrations. Thank you for your patience and attention.
Thanks, Professor Selvan. Now I will request Akila to present.
Yes, I have stopped presenting. Yeah.
Yes, sir. I'm presenting now.
And I'm not seeing.
Akila was, yes.
Yes.
Are you able to see my screen, sir?
Yes.
Yeah. Good afternoon, all. I am Akila, Selvan sir's PhD scholar. I'm currently working on RCS reduction metasurfaces. Today I will be demonstrating few of the concepts which sir has discussed already now. I'll be starting with array theory. That is, for an array, how the radiation pattern could be obtained visually using a MATLAB code. So while sir was explaining, he explained what is an isotropic source, and when the two isotropic sources are placed next to each other, like at a spacing of about lambda by 2, what happens, and when it is having a phase shift of 0 and 180 degree. So this could be coded in MATLAB. So when we want to write a MATLAB code, two things are essential. That is, we have to get an insight of the expressions that is available for that particular concept. So here in two element arrays, two things are essential. One is the element pattern. The other one is the array factor. So array factor is given by the expression kd cos theta plus beta. And here I'm going to demonstrate using two element patterns. One is the isotropic pattern. So let me run the code. Here, an isotropic pattern, as sir mentioned, it radiates uniformly over the entire space. That is spherical pattern. In two-dimensional, it looks like a circular pattern, and since it is normalized, you have an unity amplitude. And this is the array factor when the spacing between the two elements is lambda by 2 and the phase shift between the elements is 0 degrees. So the array factor is like this. The radiation pattern is obtained by multiplying the array factor with the element pattern. So these two are multiplied to obtain this overall radiation pattern, which looks similar to that of the array factor because we have an isotropic source. Now, this demonstration below is that of a Hertzian dipole. So when a Hertzian dipole is placed along the y-axis, the radiation is like this. So this is the element pattern. Again, the array factor is similar when there are two elements, which is lambda by 2 apart, and the phase shift is 0 degrees. When these two are multiplied together, we get a radiation pattern because the array factor and the element pattern was different. Here we had a isotropic pattern, so it was similar. Now the code will be running for when the phase shift between adjacent elements is 45 degree, then this is that of an isotropic source. So the radiation pattern. So this particular radiation pattern here represents that of a for beta equal to 45 degrees. The next is when the phase shift between adjacent elements is 90 degrees. For an isotropic source, this is the pattern. And for a Hertzian dipole, the array factor will be similar. The radiation pattern varies because we have the element pattern as different. Now, this particular plot is when beta is equal to 135, that is between the adjacent elements, and this is the radiation pattern. Here, this is the element pattern, this is an isotropic, and where here it is a Hertzian dipole. The final thing which sir already has discussed is when the phase shift between the adjacent elements is 180 degree. When we saw 0, the pattern was along the y-axis, like how it is in this particular shape. So these are the patterns. This is for a Hertzian dipole. Now, when the spacing between the elements is lambda by 4, what happens? The array factor changes. So the array factor earlier was different, now it has changed, and then when it is multiplied by the element pattern. So let me show a comparison of these. The first figure, this shows the array factor when the spacing between the this particular pattern is, if you see, the beta is 0, whereas this particular pattern, it is beta equal to 180 degree. So totally there is, as sir explained, the maximum radiation was in the broad side in case of beta equal to 0, where it became the other opposite direction when the phase difference between 180 degrees. So this was explained by sir in his talk. So now this 2-element array is extended to an n-element array. In this particular case, I have chosen the spacing between the elements as lambda by 2, and the array factor, when it goes for n-element array, it becomes sine n psi by 2 by sine psi by 2. Here also the plot is going to be plotted for isotropic pattern and for a Hertzian dipole. So this particular thing is when beta equal to 0. So you can see how the beam shifts when the phase is varied from 0 to 180 degree. So how does it shift as the phase is varied from 0 to, so now it is 90 degrees. Now it is 112.5, how the beam gets shifted when the phase shift between the adjacent elements is varied. So now as it goes towards 180 degree, it goes to the other side. Whereas if we look into it, the beam has broadened. So initially when we saw the beam at 90 degrees, it was very narrow. Now as it was away from the, as the phase shift varied from 0 to 180, the beam got broadened, which could be explained by using this particular, now we can actually do a change in the lambda and see, but I'm just going to the next one for a binomial array. A binomial array is one where we will not be able to produce any side lobes. The side lobes will be minimal in case of a binomial array distribution. So in this case, this code calculates how the elements has to be given amplitude. So this is the amplitude distribution when the number of elements is 10, and you could see this is the where there is no side lobes, whereas when we looked into the other patterns we had the side lobes. So the array factor doesn't have any side lobe. Finally, so these codes for 2-element array, n-element linear array and binomial array, the code was written by me, which is very simple. And when sir taught this to ME class, this was given as a task for them to do, for the students to write their code on their own. So when they started writing it, they actually enjoyed it and they were like excited to see the results. They were just excited to let that like an electromagnetic problems could be visualized like this. So they were very happy to see the results when they were able to write their code on their own. So this was very helpful for them to understand the concept. Finally, I would end up with polarization, which has this code, which I took it from mathworks.com, which should show the polarization concept. So initially, when it is horizontally polarized, in horizontal polarization, the wave would traverse along the x-axis. That is, the E field would be along x-axis. So that could be observed here at one single point, any single point. If we look into it, the variation will be along that particular axis alone. So that is shown at this particular thing. And this is how the wave, the electric field is shown here. And when we have a vertical component instead of a horizontal component, when we have a vertical component, how does, so now the E field would be along the y-axis, which should be shown now. So now it would be like this. This is vertical polarization. Now, when it is circularly polarized, uniform amplitudes would be given, and there would be a phase shift, but in this particular code the phase shift will not be provided, but here there is an option to select left hand and right hand circularly polarized, so LHCP. So when I stop it and then run it, when it is left circularly polarized, it would be on an anti-clockwise rotation when we look into it. So at one particular point there will be an anti-clockwise when we are looking into it, and then when we go for a right circularly polarization, it goes in the clockwise direction. So the direction is reversed. So all these 4 types of polarization could be observed, and even elliptical polarization we can observe by changing the amplitude. When we go for elliptical polarization, it would be the change in amplitude. So we could observe that the locus that it points would be an ellipse, and then this is to elongated along the x-axis. When we want it along the y, so we can change the parameter over here, and then so that the elliptical polarization could be demonstrated. So these are the things that we can use a MATLAB code to visualize a particular concept which has been taught in the class. And the array concept was already like in Sir's class, it was being demonstrated. So this is how a MATLAB code could be used to visualize particular concepts.
Yeah, thank you very much, Akila. Thank you, Akila.
Thank Professor Selvan for this kind of approach, so that faculty members are aware that there are many ways to do this, as he was trying to say, and there are many resources available. He has also identified a few, and through the slides, people will be able to see some of these simulation sites that they can be used profitably. And also towards the end, I think the student was trying to say that you could yourself code with a little help, and the rewards are very disproportionately large, I would say.
So let us thank Professor Selvan on behalf of IIT Madras, on behalf of ACT QIP short-term course, and on behalf of the participants, and on our personal behalf. I would like to thank both of you. Okay, for sparing time with us.
Yeah. Thank you very much.